Uh, well, okay. Good morning from Chile to everybody. And that would be a good afternoon in India. And perhaps in Hong Kong, where I have some friends, that would be a good evening. The time difference with Hong Kong is 12 hours, with India is 9:30 hours. So it's extremely, well, it's something very special actually, because we are getting together, although this time difference. Well, Professor Anbarasan, he's a great scientist. There is no doubt about that. And he's going to talk about focal engineering in solar cells. And every curricula vitae said that Professor Anbarasan worked at the Department of Physics, Periyar University. This is Salem, isn't it, Professor? Salem, India? I think so. And his area of interest are laser physics, nano-optics, solid-state physics, condensed matter, and computational physics. He's a very distinguished scientist, actually. His research gate score is 35.24. And as far as I could see, he has something like 174 peer-review work already published. And he has a large number of quotation or citation, and over 1,000. So it is a real pleasure to welcome Professor Anbarasan. And let me say that I'm very grateful, because I think that all the scientists from India have done a great job and are helping us a lot, actually. This is going to be on YouTube soon, in Facebook and LinkedIn. And I'm going to send you, Prof, the link of this talk when this is over. So please welcome once again. And please, as usual, do remind me to your family and beloved people. And I hope that we shall meet personally very soon. Professor, you can start as soon as you want to, please. Go ahead, you can share your screen. Now.
Is it sharing your screen? Is it visible, the slide?
Well, I see your face. You have to share the screen.
Yes. Now we have your face.
Yes, you can share the screen, huh?
Okay.
We're getting ready. Yes, now we are ready.
Is it visible?
Yes.
Yes.
We can see very, very well.
Just a minute, it is loading.
Yeah, we're okay, yeah?
Professor, is it moving to next slide?
I can see the slide. Okay. Yes, now it's working.
Hey, yeah, okay.
May I continue, Professor?
Now we're fine.
Okay, thank you. Just I took some time to load the slides. It takes some time.
Yes, it doesn't matter. We have time, Prof.
Okay, shall we start?
Yes.
Well, it's up to you. You can start as soon as you want to.
Yes, yes. So this is the outline of my talk. That is focal engineering in solar cell. So it starts with optical engineering.
Okay.
It is nothing but a field of science and engineering incorporating the physical phenomena and the technologies associated with generation, transmission, manipulation, detection, and utilization of light. So in this way, our talk is focal engineering. It focuses light. How the optical engineering playing in the field of solar energy. In my earlier talk, I have given the title of sophisticated laser for nuclear waste management, that mainly focusing on laser light. That means tight focusing of laser light. It leads to how the extreme light intensity can be produced for making use of interaction with the radioactive element. But my earlier talk is based on laser. It is a coherent source. But in the case of present talk is sunlight. It is a incoherent source. The first one is coherent. The second one is, now we are talking about light trapping scheme of sunlight. Earlier tightly focused laser beam. Now how we can trap the sunlight. This is the way in which many new technologies are emerging that capture and redirect sunlight into the solar cells. This type of light management are significantly increasing the efficiency. But in the same way, the device behavior will fundamentally depends on the spatial coherence of incoming light. So in this way, this dependence for a complete characterization of sunlight must be discussed. This sunlight is being utilized to reduce energy crisis nowadays. And this solar energy is a popular and reliable source of energy because of its pollution free in nature. So it is abundantly available on the earth, but difficult to achieve the maximum efficiency. That is the drawback behind the trapping of sunlight in solar cells. So this is also important to reduce the environmental pollution. It is necessary to generate electricity by means of new and renewable energy sources. So one of the most promising this green energy source is the sunlight is the most important. This can be harvested for generating energy successfully by means of some light trapping scheme. So far, the photovoltaic based electricity generation has been very successful, but average efficiency of the energy conversion is low in the case of polycrystalline silicon solar cell photovoltaic model. However, the efficiency of the solar cells based on thin film multi-layer structure can increase the efficiency up to around 40%. This is due to the fact that there are number of ways. Many panels are using trackers. When sun rays from east to set in the west, there are some trackers are used towards the sun where it moves. Some trackers are used to trap the motion. So in this way, our research work is based on, there are two cells. One is silicon solar cells, another one is dye-sensorized solar cells. How the solar cell can be fabricated with a more light trapping scheme structure. So in this way, we designed the upper surface or the front surface of the solar cell having with the V-shaped groove. Apart from that, that means in addition to, besides we have fabricated the planar as well as cylindrical type micro lens to trap more or concentrated light to fall on the device. So in this way, the design of micro lens coupled with the V-grooved silicon cells, and also that the other part I am going to discuss about dye-sensitized solar cell, DSSC. So how we can select the dye based on the computational facilities using the software density function theory and time dependent density function theory, we have formulated to select the HOMO-LUMO values of the dyes. So based on the computational study for selection of dyes, we fabricated the different naturally available dyes. There are two types of dye sensitive solar cells. One is metal based dye sensitive solar cell. Another one is metal free. That means without ruthenium dye. See here we have selected more than 50 natural leaves, fruits, and other stem, whatever it is. We have collected so many naturally available extracted dyes from the plants. So how it works, and also we have performed the efficiency. Next, we have compared these two solar cells, silicon solar cell as well as the dye sensitive solar cells. Compared which one is the best one using the same setup of experimental procedures. Then we have also studied how the heat transfer taking place in the device, and also when the light is falling in the form of irradiance, how the irradiance changing, how the efficiency also changed, and the angle of incidence also taken into account for both the silicon as well as dye sensitive solar cells. The next one is analysis of focusing properties with it. So this one, we know very well that the important relation is S equal to Z naught divided by cos theta. When the sun is at the east, it is making to sun at the zenith. So there is change in angle theta with the correlation S not equal to Z naught by cos theta. So this is the things we can identify the air mass factor. So there is no direct way we can say that without any dust free atmosphere available, that is called air mass 0. But the increasing the dust particle in the atmosphere, we can go for AM1, 0, AM1.5, AM2, like that. From country to country, this air mass values will change. So in our photovoltaic applications, the trackers are used to minimize the angle of incidence between the incoming sunlight and the PV panel. So this will automatically increase the efficiency of the cells. So it is estimated that this kind of trackers are used with at least 85% of the commercially available solar panels in the market. So in this way, the tracking systems are followed as a concentrator, and also this type of systems are pointed at the sun to achieve the maximum efficiency. So this is the things, the schematic diagram showing one software we used to find the ray tracing method. There are two types of methods are used, the scientific version as well as the engineering version are used in the software is called ZMAX. ZMAX is nothing but one scientist, he coined the word by his dog name, that is ZMAX. So this ray tracing method is used. There are two types. One is sequential ray tracing method. Another one is non-sequential ray tracing method. If the set of source, optical element, and screen are in the same plane or same in the direction, it comes under the category of sequential tracing, ray tracing method. If the optical systems and the source and screens are somewhere away from its direct ray, that can be identified or the analyzed by the another method is called non-sequential ray tracing method. So in this way, we have used sequential ray tracing method for identifying the position of the sun with a different angle. When it is in the morning hours, that first slide showing that it is morning hours. This one is noon at the 12. So this one is evening. So here we have followed without non-tracking method. So within that, there are many new technologies are used with and without tracking, and also that many concentrators also used for trapping more sunlight to concentrated sunlight to falling on the solar cell device. So this is the things you know very well that the sunlight reached on the earth surface having that range of 40 to 45% with visible region in the wavelength of 380 nanometer to 780 nanometer. This one 380 nanometer to 780 nanometers, and 50 to 55% of IR radiation in the range of 800 to 2500 nanometer, about 3 to 5% of UV radiation. So this irradiation data for our region Salem, which is in the state of Tamil Nadu in India. So this irradiation graph we have obtained from Meteorological Department of South India, which is provided this data. So this gives, I will give you one more, and these are all that how many irradiations from January to December. The average we have taken 5.24 kilowatt hour per meter square per day is falling on the our earth surface in the Salem. So this is also important that how this type of non-tracking experimental setup showing that the sunlight radiation reached on the surface with that the early morning. Here this is the Fresnel lens. It is nothing but a hybrid lens. Hybrid lens means aberration free lens. There is actual chromatic aberration corrected hybrid lens. That means we can minimize the diffraction. So what will happen in the front surface, whole incident light will be trapped and absorbed to send inside the systems. So here there are 6 different mirrors are aligned to trap more light on the model. So in this way, refractively, diffractively, and also that what is that? All type of minimized aberrations are taken into account for reaching the high efficiency. Here, this is the light trapping in its to achieve the higher efficiency. The following objectives are taken into account. It must be reduce the front surface reflectivity. Otherwise, what will happen? The efficiency or the amount of light trapped will be reduced. So to increasing the path length of the device, we have to arrange more concentrated light. To increase the amount of trapped light reflected from the back surface, and the total internal reflection must be achieved. Then only we can go for higher energy conversion of sunlight into electricity. So in this way, concentrators in a solar cell designed to operate under illumination greater than 1 cell. That means 1 cell means nothing but air mass 1. So concentrators have several potential advantages, including higher efficiency potential than 1 cell solar cell and the possibility within the manufacturing on low cost. So the short circuit current from a solar cell depends linearly on the intensity of the light falling on the surface or front surface of the device. So in this case, here how we have simulated the cylindrical microlines to achieve that more concentrated light to trap on the model. So this is the things that our aim is to improve the light trapping efficiency of V-grooved thin silicon solar cell by using either cylindrical or planar microlens as concentrators. So in the cell, V-grooves are positioned in such that the coupled light passes through a V-grooved solar cells that misses the adjacent one as it travels to the bottom of the cells. One face of the V groove is coated with aluminum so that the light reflected off this face would be coupled into the cell through the opposite face of V groove as illustrated in the figure you see here. You see this is the incident light falling on the V groove. This is the V shape. So what is happening? So total internal reflections are taking place to trap more. This geometry of V shape in solar cell is designed to trap light by serving as an optical funnel. It is like optical funnels. As a result, photons falling on the front surface having multiple interactions within the solar cells. The active layer of the cell is very thin compared to the substrate of the designed geometry. So here, this is the things. Moreover, when you are talking about silicon solar cell, it is nothing but the photons in sunlight hit the solar panel and are absorbed by the semiconducting materials to create electron hole pair. So this electron hole pair in the form of negatively charged are knocked loose from their atoms, allowing them to flow through the material to produce or the conversion of sunlight into electricity. Here, this spectra showing that how we have manufactured many different thin layered silicon solar thin films, which are ranging from single crystal to nano crystal to amorphous state. Why we have taken these varying structured thin planes? Due to that, when you are changing the different grain size in the thin flames, automatically what will happen? The more wide range of spectrum can be trapped. You mean when you are changing this one optical band gap energy depending upon the particle size present in the different structured thin planes. This wide range of solar spectrum can be trapped for getting conversion of sunlight into electricity. So in this way, this is the metal contact surface. This is the sunlight falling on the front surface. This is the different stacked thin planes which are having amorphous versus nanocrystalline, then single crystal. These are all stacked together to trap more of increasing order of size of the thickness of the thin films. So again, it is transparent conductive coating material PCO. Then this is the glass substrate. These are all the designed for silicon solar cell. The substrate size we have 1300 by 1100 square centimeter. Here you see that this is the things. This is the structure of, this is the front surface and back surface, one layer. One is anode, another one is cathode. In between the layers, how the p-type and the semiconductors having that. Actually, it is having one animation technique. Why there is no possibility working on it? I don't know how to change. This is it is framed using that some animation technique. How to change this one animation one? It is directly showing that slide without a PPT mode. I think. How to change into PPT mode? Not going. Okay, late. So I don't know why this one is missing. Any other applications? Okay, no problem. Many things
Okay.
we may miss. I don't know how to display that animation one. Okay, next. These are all the big road thin solar cell model by the geometry structure. So this is also the scanning electron microscope picture of the cross section of the patterned surface of silicon wafer, revealing the shape of the micro lens. So this is the thing we can discuss now. This is the planar structure of silicon solar cell. We have designed the micro lens, planar micro lens on the top of the structure. So when you are talking about the next one is called how the incident light falling on the front surface of the micro lens. The more lights are concentrated, lights are trapped by this micro lens to send inside that device, the substrate. So these are all the geometry we have discussed. Here, the next one is, you see, this is the plane surface with the micro lens, more steering light are going inside. This flat type silicon solar cells with micro lenses as concentrated for efficient trapping. Here there is some reflection will also taking place. Automatically the efficiency will reduce. For that, we have formulated that V-grooved solar cells. Here, I told you that this is one type of V-groove. The electrons are excited from this. There are atomic orbits. Once they excited, the electron can either dissipate the energy as heat and return to its orbital, or travel through the cell until it reaches an electrode. So the current flows through the material having some potential and its electricity is captured. This one. You see, this is the things V-grooved silicon solar cells with the micro lens. This is V-grooved. This is the micro lens. So what is happening? So total internal reflection taking place within the device, for more concentrated lights can be sent inside the device. So next one is, this is the micro lens. It is acted as a concentrated for trapping more light. So this is the V-groove reflector. It is aluminum coated. This one reflected inside opposite. There's the arrangement you can easily check with the another one. This one, you see, This is the micro lens. This is the V groove. So what is happening here? The more concentrated lights are sent through the aluminum reflector. Everything is going inside that device. So this is the thing we can easily understand. So this, for that we need more optical engineering. So here
Well, we have to wait. I think we are having some connectivity problems. And he's going to come in again, I think. Yes, now we're fine.
Produces groove, depende del groove.
We're fine now. They're trying to fix the problem. No, we're fine now. We're back.
The first slide.
yes, first slide. Is it moving now? Slides are moving. Hello?
Yes, I hear you now. No, it is perfect.
Can you hear my voice?
Very
Is it
well.
audible now?
Yes, very well. Carry on, Prof.
Yes.
Is it moving now?
Yes, it is
Yes.
moving. Yes.
Okay.
Okay. Right. Is it? The minimize பண்ணிக்கலாம். Thank you. அது வந்து ஆட்டோமேட்டிக்கா மாறிடும். இல்ல அது வந்தா மாறிடும். ஓகே. ஆமா. So this one I told you earlier how the physics of photovoltaic generation taking place. So you see, this is the things we have discussed earlier. You see,
Yes. The p-type
this
and
is the n-type
yes.
semiconductor.
Yes.
P-type semiconductor. This is the depletion layer in between the.
Yes.
These are all the things. When sunlight is falling in the form of photons on the surface of the solar cells. So this one is the basic things. What is happening? The charge carriers are moving. The holes are moving in this direction and the electrons are moving in the other directions. So this is the simple basic structure of silicon solar cells. So in this way we have discussed but unable to change into PPT mode. Now it is okay. So the PN junction, you see, this is the things we have discussed. So the solar cells are essentially semiconducting junctions under illumination. Light generates electron hole pairs on both sides of the junction. The generated electrons and holes then diffuse to the junction depletion layer and are stripped away by the electric field, thus producing electric current across the device. This one. So this PN junction therefore separates the carriers with the opposite charge and transform the generation current between the bands into the electric current through the junctions. So this is the things we have already seen. You see, this one also we have seen earlier. You see, so this is the how to according to our geometry we can reshape the structure. This is nothing but the ethyl vinyl acetate as a base is used to combine the V groove structure and micro lens. Why we are using the ethyl vinyl acetate is there is no change in the refractive index of the material medium. Both the EV and the micro lens, both are having that same refractive index. So in this way, we can arrange or align the micro lens above the V groove structures, so that we need some mathematical expressions which we have already discussed. So already I told you that using the software ZMax or in the MATLAB, many applications are used in this device geometry. Here, this is the how that range of V groove. Here, the coated aluminum surface. This is the another one is open surface. All the reflected lights sent through this another space to making use of the conversion part. So here, the geometry of A, B, C, D, everything is no. This is A, B, C, D, E, F, G, H. These are all the angles parameters we have taken. So this is the thing. So we have calculated the lengthy equations for identifying that how above the distance required for align the micro lens. So this is the optical path is also calculated. It is the 2 times of width of the this V grooves we have identified, and also that we have measured the quantum efficiency of V groove. This one is planar cell without microlens, V groove with the microlens, planar with the microlens, V groove with the microlens. So the highest performance we achieve the quantum efficiency for V groove with the microlens structure. So this is the result saying that the V groove thin lens solar cell modify the geometry of the cell to permit multiple reflection and enhance the absorption. So here the V groove structured shape making use of the maximum efficiency of 38%. So what will happen? The reduction in reflection loss by using the V grooves is achieved. So here the V groove reduces the reflectivity at a small angle of incidence due to multiple reflections within the cells. So next one is for our comparison, we have taken dye sensitized solar cells. So this is nothing but it is having basic 5 components. Very important that within the few rupees in Indian rupee, within 1 rupee, we can fabricate this solar cell. That is the peculiarity in making this dye-sensitive solar cells. There are 5 components are involved. One is photoanode, another one is mesoporous semiconductor. Here, titanium oxide is used, KO2 is used. Then we have used this dye sensitizer, natural dye. The more than 50 types of naturally available Indian plants extractions are used as a dye sensitizer. Here, the electron hole transporting material is iodine is used. Here, counter electrode is platinum is used. You see, these are all the metal-based dye sensitizers. Ruthenium-based dye sensitizers, but automatically gives more efficiency, but it is cost effective. It is very costly, and also the total manufacturing prices high. So to avoid that, we are selected metal-free sensitizers, dyes as dyes. So the basic architecture of this one is it must be one donor and acceptor in between some spacer. Pi conjugate is used to combine this donor and the acceptor. So here, for that, to design the die architecture units with the use of appropriate donor and acceptor modalities. So we have taken density function theory and the time dependent density function theory, DFT and DFT calculations are used for identifying the best die for the fabrication of die-sensitive solar cells. To understand the structure and the property relation, using the following parameters are obtained for our calculations. So this one is geometric structure, natural bonding analysis, electronic structure calculations, spectroscopic features, dipole moment, and the polarizability and the hyperpolarizability. Why these two we have calculated means, so after if it is not used for dies efficiently, we have switched over to analyze the NLO property of the die. So that we have also calculated the dipole moment and the polarizability and the hyperpolarizability. So in this case, the computational details are showing that this one is very lengthy one. To avoid that one, we skip. This one also, the higher polarizability and the hyperpolarizability formula for analyzing the NLO properties and also for solar cell properties. Here you see that our many samples we have collected as a natural sensitizers. This one you might have seen in India, that is called henna leaves, where the most of the ladies in our India apply on the palm, coloring in our palm, in hand, in the inner part. So this one is a leaf. It is used for food. This one is finance. This one is also important one. So these kind of different colors we use as sensitizers. So these are all some of the sensitizer used for the fabrication of die-sensitive solar cells. This is grapes, then amla, then neem, the cabbage, many things. The different colors having different absorption taking place from the wide range of solar spectrum for trapping the sunlight. So these are all the different naturally available fruits, leaves, and stems. Many even stems, fruits, different things we have analyzed depending upon the colors available. Pomegranate and also many tulsi used to call one type of leaves that is used for medicinal purpose in our India. These are all the and some of the natural sensitizers. This is the turmeric and also variety of turmeric. These are all turmeric, but having different traditional values. So this daughter turmeric, bigger turmeric, current turmeric, like that, there are some classifications. All having different efficiency, due to its structure and also the curcumin behind in the turmeric. So these are all the saffron flower and chemical structure. So these are all the way of extraction taking place from the natural dyes. The photograph is the extracted dyes. So this is the designed dye-sensitive solar cells. You see, these are all the preparation way how we extracted from the naturally available what is that items, and these are all the way in which these extra things we have to, because our area is only focusing engineering. So for that we need some of the basic information for the preparation of solar cells. So we skip the flow step also. We are going to skip because we are how to discuss only about this DSSC. So this is the fabrication technique. This one is anode. Another one is the both sides are blacked by the any insulators like cello tape. So this is the TiO2 paste. Semiconducting TiO2 paste is applied in the process. So this is the roller. This paste is that is smoothed by the roller. Again, one more things we have taken another cathode. This one is dye is applied on that. So again, this dye is applied. Another one is one whole transporting material, that is what is that, iodide is used. You see, this is the one more substrate. One act as anode, another one is cathode. So both are kept like that. So what is that? This is the electrode. This is the another electrode. This is electrode. This is called counter electrode. So the sunlight falling in the form of HNU photons in the dyes. This is the LUMO. This is the HOMO. Lower unoccupied molecular orbit. This is highest molecular occupied molecular orbitals. So what is happening? It is excited to the higher level, so transform to the TiO2. This is the valence bond. This is the conduction bond. Through the conduction bond of TiO2, it is reached to the cathode. That is the one electrode. Through the external circuit, it is going to counter electrode. This is the whole transporting material acceleration, the redox taking place. When the hole is created, automatically the electron will be moved to this another one. So this is the animation showing that how the DSSCs are working. So in this way, you see, this is also the simple animation showing that how the electron in the form of the photons in the form of energy falling on the dye surface. This is the dye surface. So again, this electron is moved to the upper, that is where band. Again, it is the electron is transferred to TiO2 semiconducting so this is again, it is going to the external load. It is going to counter electrode. After that, that is after reaching that platinum counter electrode. Please. Here full rain is going on. Okay, so this is the dye electrons are excited by the solar energy in the form of sunlight photons. So absorption taking place through the dye. So they are injected into the conduction band of TiO2, get the counter electrode to the cathode through the external circuit. The redox regeneration of the counter electrode oxidation takes place. Then dye regeneration reactions by the reductions, the potential used for external load. So this is the things how our electron transfer dynamics. The same things. This is the electrode, counter electrode. This is the dye. This is the TiO2. This is the mode transporting material. Redox and the oxidation taking place. So this must be the important. This Fermi level of this values must be higher than that, lower than that dyes HOMO values. This must be the LUMO values must be lesser than the band gap of this LUMO values of that dye. That is the important factor. You have to find out while you are selecting the dye using the computation technique. That is density function theory. That is the things we have identified first from the naturally available dyes. First LUMO, HOMO, and these values are important for designing such things. So these are all the heat treatment of photoanode. then how these things are fabricated. Already we have animated this one. These are all the fabricated solar cells taken for three for our comparison with silicon solar cells. So these are all the parameters, IV characterization studies. The important parameters are open circuit voltage, short circuit current, and the fill factor, overall conversion efficiency. So this fill factor is multiplication of voltage maximum and current density maximum, open circuit voltage and current density. That is this one. So in this short circuit, JSC, the VOC is important. So the efficiency is VOC into JSC is by that is incoming power in the sensor. So this is the stimulated sunlight values is 10 milliwatt per square centimeter for our experimental setup. We have generated to the simulator. So this is the IV characterizations plot showing that how the maximum P maximum is identified. So here, this is the photovoltaic parameter of BSS sensitized by using different photoanodes. So we have different photoanode, ZNO based TiO2, aluminum TiO2, DiTiO2, MgTiO2. So what will happen? This VOC, JSC, Vmax, and Jmax, and the fill factor efficiency also changing. But also it is very less, lower values of efficiency, but comparatively good in the case of cost effective with the silicon solar cells. So this one photovoltaic parameters of PSS sensor using different anodes. So the same things we have carried out when the increase for different dyes which are available, naturally available in India, particularly in Tamil Nadu, in our area. So these are all the different types of cell types, and also we have changed the irradiance. That is how much of light falling on that surface. That is 48 watt per square meter, and 67, 115, 165. Like that, we have changed the intensity also. By having that 20-degree angle of incidence, 40 degrees, 60 degree, 80 degree, like that, we have moved. So in this way, we will see fill factor and efficiency. You see, we have compared this up to this one, this DSC1, DSC2, DSC3. This one is flat type silicon solar cell. The same things we have carried out, but the efficiency also increased. So if it is flat type, it is around roughly 17 to 19.8 efficiency, percentage of efficiency. When you are experimenting with without microlens of the V groups, that is also increased somewhat from flat type. When you are going with the V groups silicon solar with the microlens, we achieved maximum roughly 19% and above. And also there are some problem when the light is traveling through the different mediums like lens as well as the ethyl vinyl acetate base. Due to that, some of the error pattern also appeared. So that we sometimes we achieved 19.8 also in the vortex silicon solar cells. And also the intensity also high. Because of that also the values also increased. So these are all the comparative study between the silicon and the dye solar cell. This is the monochromatic silicon, this is polycrystal silicon, this is thin films. So here is the thin films is taken as a different thickness of the thin films, wide range of increasing order of thickness, that the grain size also will increase because of the changing of optical band of energy. The wide range of what is that solar spectrum can be trapped. For that, we stacked many solar thin films. So in this one, the comparative study between silicon and the dyes and solar cells. Here, this comparison is also taken into account with the angle of incidence, irradiance intensity, and cell temperature. So the problem is when the temperature increases in the silicon solar cell, the efficiency decreases. When the temperature increases up to 60 degrees, the dye sensitized solar cell efficiency also increased linearly. Up to 25 degrees Celsius only, the silicon solar cell showed, that means obtained maximum efficiency. So in that case, the simple calculation is used the following relations for transmittance, absorption, and reflectance. So it must be totally unity. So that calculation is taken into account for calculations. So this heat transfer study also performed for that fabricated silicon solar cell as well as that dye-sensitive solar cells. So what is happening here? This setup consists of a xenon lamp as a source is used to imitate the sunlight. We have used the xenon as a source. So with some filters, so like to create the atmosphere like air mass 1 or 1.5 like that. So this is also one mirror is kept at 45 degree with that to distribute the illumination on the test area. So here this is the test area, and the fans to avoid heating the cell also arranged. So irradiance intensity at the test area is measured by standard silicon ionometer. So this cell have a different spectral response than dye-sensitive solar cells. So here the reflection measure for irradiance levels at the test surface, which ensure comparable test conditions for the cells. Here, the spectral distribution of xenon lamp compared to solar irradiance is 1000 watt per square centimeter and the real mass condition of 1.5. So the peak intensity of the source, light source, that means xenon lamp is found around 550 nanometer average on an average. So this is the testing setup with the silicon as well as dye-sensitive solar cells. So here the tracker also used instead of varying angle by the other setup which was shown in the earlier second slide, I think third slide. So this is the experimental setup in our Periyar industry. So how we have solar cells, the maximum power point also identified by the relation PM equal to VM and I. This is the three factor open circuit voltage and the short circuit current. The average temperature also identified these calculations. So this is the investigation of heat transfer in photovoltaic model. So this is the source, any kind of source, and this is the system array. This is the panel. How the spacing between the gap walls and the thickness of rear side. These are all the parameters used for analyzing the heat transfer study within the device. To investigate the heat transfer in photovoltaic models, so this type of equation is used for identifying that what is the temperature. So this one also heat transfer. This is the incident light falling on the front surface of the dye-sensitive solar cells. I know this is the electrode. This is the counter electrode. This is the semiconducting material. This is the dye. This is the whole transporting material. This is the another one. That is the harvesting whole transporting material. This is the electrode. Okay, this is also the total thickness is taken into account of 4.4515 millimeter. This net substrate of measurements or parameters. So here again the performance of parameters for various solar cell at G values, irradiance values is 1000 watt per square centimeter. So many types of solar cells they have aggregated and measured the IESC, that is short circuit current, open circuit voltage, and fill factor P maximum. With that, the efficiency also calculated with the naturally available natural slice. Similarly, with the many silicon solar cells also we have purchased put in manufactured. We have purchased from China, and also these types of silicon varying values of parameters, and also identified that different efficiency with the different fill factors. So this is the effect of irradiance and the temperature. We also measured the irradiance temperatures. So the effect of temperature also we have measured for both the dye-sensitive solar cell and as commercially available microcrystalline part-type silicon solar cells, B-groove silicon solar cells without microlens, the B-groove silicon solar cells with the microlens have been carried out under controlled air mass conditions. So these are all the tilt measurements. When the whole apparatus is tilted to 45 degree, 20 degree, 10 degree, 60 degree, up to 60 degree, we have measured that efficiency with the conditions that overall overview also changed. So this analysis says that the solar radiation data and the amount of solar intersects the specific area are essential for modeling the solar energy system and covering the demands. So this values from the meteorological department of India, they provided that values how much of sun falling on the earth surface of Salem, South India. So from January to December, average we had taken 5.24 kilowatt hour per square meter. So these are on IV characteristics of various ingredients with intensity for different types of solar cells. This one we have seen. So this is the thing also we have discussed. So the V-grooved thin film solar cell modified the geometry of the cell to permit the reflection and enhance absorption to avoid the reflection and enhance the absorption. So the V-grooved plane, the maximum efficiency we achieved 88%. The reduction in reflection loss by V-grooves. The V-grooved reduces the reflectivity at a small angle of incidence due to multiple reflections within the device. So this device structure having its technology is to making use of wide range of solar spectrum to convert that maximum efficiency. That means solar energy conversion to electricity. So this study performance of solar cell using this design is the scope for future work. So which he conclude that only up to 25 degree centigrade the maximum efficiency in the solar cells. Up to maximum 60 degree centigrade, the silicon, that is dye-sensitive solar cells increased the efficiency. So that is the conclusion we have identified. The experimental results seen for the dye-sensitive solar cell favor low irradiance, whereas the highest conversion efficiency taken into account. This mainly due to loss of reduction in cell under low irradiance, where the number of recombination and the charge transfer resistance is low. So this amount is relatively high fill factor for the DSSC at low irradiance. So this is also conclude that as the relative open circuit voltage and the fill factor is seen to decrease the angle of incidence for both silicon and the dye-sensitive solar cell in the relative of maximum power, which is seen differ up to 28% for DSSC. So they expected power output of 25% for DSSC and 40% for silicon solar cells. So this is the experimental setup, fabrication of dye-sensor solar cell in our Periyar University. So this is the also the V-groove technology and how that optical engineering taking place with the help of Professor Dr. Roswell Karuli, head laser group department of optics and quantum electronics, the head university Hungary. So which was sponsored by Indo-Hungarian Education Exam. While I was working in Hungary, I carried out some of the experimental part.
Well, I had to say that it has been a wonderful lecture, Professor Anbarasan. And of course, there must be a lot of questions to be asked to you. And I would like to ask if Carlos has something to say, or he wants to make a point, or has some doubt, or whatever. Carlos, you can carry on, please.
Yeah, that was a long time ago anyway. So almost everything is forgotten at present. But anyway, I have some questions. This, as far as I understood, one of the main enhancement of current cells are this special surface, the structure, which allow many reflection inside the systems. Now, are you trying this, or are you trying trying this type of cells outside? I mean, in open sites, are they used in some practical application at present? I'm asking this because we in Chile, as probably you know, we have a high solar radiation, one of the highest in the world. And this solar radiation is mainly in the northern part of Chile, where we have a very large desert with very high solar radiation, extremely dry atmosphere, and many places where they are used are high altitude, 3,000 and more meters above sea level. Now, one of the problems concerned with these technologies is soil effect, heating, and low pressure. Low pressure is affecting the transformation of continuous current, DC current coming from a cell, to alternative current, which is used in industrial problems. So these are the main problem. Actually, it is what I know. Huh? Do you know something about that? Soil effect, high temperature, low pressures. Have you studied something like that in this type of cells?
You couldn't hear. Hello?
It's communication problems. Carlos, he did not hear you.
Professor Anbarasan, didn't you hear me? Should I repeat?
Yes. Hello?
Should I repeat my
Yes, please.
Okay. What I was saying is, in summary, is this. As far as I understood, one of the main points in your conference, which anyway is very interesting, my congratulations, very interesting. One of the problems is the enhancement of efficiency by doing a special architecture of the surface, this surface, which allowed to use inside reflection. It's okay with me, very interesting. Also, what you have talked about the dyes. Now, here in Chile, we have a very high solar radiation, I guess one of the highest world radiation. And the problem, and this solar radiation is mainly located in the northern part of Chile, where we have a very large desert, I guess the driest desert in the world. And the problem concerning the use of solar cells, photovoltaic cells, is soiling effect, the problem coming from dust in the desert, which decrease the efficiency of the cell. And that's one problem. The other problem is that we have a lot of infrared radiation, which means heating, of course, and also a low pressure, atmospheric low pressure in the places where they are mainly used, because our copper mine, which is our most important economical sources, are located at maybe 2 to 3 or 4,000 meters above sea level. And then we have a problem with the converter of DC current to AC current. And my questions, which are 3, is: are you focused, or have you attempted to study these type of problems, or not yet?
You mean conversion of DC to AC?
Pardon?
Your question is DC values or AC values?
Yeah,
VOC and JAC.
You know, because the energy produced by the photovoltaic cell is DC current, right?
Yes.
It needs to be converted to AC current, and the converter is affected for low atmospheric pressure. So that is one of the type of problem they try to solve it. Another problem is soiling effect, because we are in the desert where there are a lot of dust. And the other is because with this high radiation, we also have a high infrared radiation producing this heating effect, which anyway you have face it in your work. Then my questions were if you are concerned with this type of problems or not yet in your studies.
Can you hear, Professor?
Yes.
Yeah. Perhaps you cannot hear well what Carlos is asking you. Did you hear him?
Hello.
Could you hear Carlos? Now, let me say something. Can you hear me? My voice?
Yes. Couldn't
you
hear
can.
that.
Can you hear me? Can you hear me?
Hello.
Can you hear Carlos?
Yes. Hear your voice. I couldn't understand the question raised by.
Yeah, Carlos, he did not understand the question, actually. You can make it short, huh?
Okay. No, I'm just saying that in Chile, there are some research, important research on these photovoltaic cells. And the main problems we are facing with this type of cells is soiling effect, because they are located in desert where there are a lot of dust. Also heating effect, because there is a high infrared radiation, and also loud atmospheric pressure, which produce a problem with converting DC to AC currents. My question is if you are facing this type of problems.
Your part is mainly on the conversion of DC to AC. The converter is used. Am I correct?
Pardon?
Your problem with the converter are the irradiations. With the place to place, the irradiation effect will change.
I don't know. I don't know anyway why that problem occurs, but I know that it there exists. The problem with the conversion from AC to DC, though maybe it's not a problem of the photocell by itself, but mainly the soiling problem, and the infrared, the heating effect.
Heat effect.
Yeah.
Am I correct?
Yes, heating effect because of the high infrared radiation.
Yes, the temperature, cell temperature increases, the efficiency decreases in the
Yes.
silicon solar cells.
Yes.
If the cell temperature increases with the increasing of efficiency in dye-sensor solar cells, that is the complication between these two solar cells.
Yeah.
Yeah.
Okay.
Now we understand, I think.
Yeah.
Professor Anbarasan, this subject of yours, of your talk, is very sexy. I will say in English, a very sexy subject. And many people you see are trying to do something about this area of research. If you could give us an advice to us and to many people, what would you say? How people or what people should be doing to advance the state of the art in this area? What do you think? Could you understand what I said? Hello?
Hello?
Can you?
Regarding the field?
What I say is that many young people are really trying very hard to understand the subject and to do research, right? What would be your advice for them? What do you think? Well, if I mean, I could write the chat if you want.
Chat, chat.
Because you see what happened is that sometimes the communication is not very good.
Yes, yes, please chat.
What I'm saying is many people in Chile are trying very hard.
Please question through chat box.
Yes, I'm typing it. Are trying very hard to do good research in solar cell, right? This is what is going on here. Now, what kind of advice would you give them? Sorry about that. Could you give young people to continue with advanced research in this area? Because this is very important, Professor, in Chile, actually.
Many people in Chile are trying
very hard research in solar cells. Well, here it should be. What can you advise? Okay. There is an error here. What can you advise? What can you advise them to do in the near future in this area? I think this is a more specific question. Did you get it, the message?
Yes, yes. Now I am typing.
Because you see what happened is that in Chile is in the north of Chile, we have several research centers of people doing research in this area. And perhaps you can give them, due to your experience, you can give them some advices about how to continue and how to advance the state of the art in this topic. What do you think about that? What should be done, actually? This is the point.
Yes.
Yeah. A problem with solar cell research is manufacturing cost of silicons are very high. This is true, yes. In DSSC, efficiency is very, very, very less.
Yes.
I'm reading for the people who cannot follow the chats. This is a very important area of research. Yeah.
Excuse me, in Chile, we have a joint project with some German and Spanish research center like Abengoa. Have you heard about it? Abengoa, and I guess they are working on this DCSSC type of cells. Huh? Have you heard about Abengoa? It's located in the southern part of Spain.
Spain, yes.
Yes.
Well, I guess that you are asking Professor Anbarasan.
Yes.
Oh, yeah, okay. Conversion production cost of electricity is costly, and other type of neural. What does it say there? Neural. Is this renewable resources or? Let me see this word.
Renewable, eolic type of system.
This is something new, actually. This is what he is saying.
That you can renew it continuously. Huh?
Yes, yes, yes.
Like on the contrary, on the opposite to coal or fossil fuels, which end up. Huh?
Yeah.
So solar is continuously renewing. Huh?
Yeah, but you see in Spanish, renewable means novedoso.
Renovable in this case. Renewable, renovables.
Yeah, well, yes.
Yes, yes.
But you take the translation directly from the dictionary, you get novedoso.
Which is that? Which is that?
This is what you see in my iPhone. This is a translator.
Huh?
There is a translator. And this is called, yes, a translator. It is an application.
Actually, these all type of energy sources are named like non-conventional renewable sources.
Yes, renewable sources. Yes, that's very true.
Yes.
This is a very sexy subject, actually. How many people are working in this in the north area? Carlos, do you know anything in Antofagasta, for instance?
Yeah, there is you know, there is a consortium, very important consortium among the main universities like Catholic University, University of Chile, and the Santa Maria University in Valparaiso, and University of Antofagasta, and 2 or 3 others, plus some joint project with some Spanish and German research centers. And they're working, as far as I know, in 3 main topics: photovoltaic, production of energy. Eolic, the one coming from the wind. There are many, mainly in the southern part of Chile, Professor Anbarasan, because it's a very windy place. And finally, also in the north, solar concentration. I mean, there is lenses which concentrate the sun radiation in the highest part of a tower. No?
Yes,
So
yes.
some salts, mainly nitrate, are melted, and they are made circulate. They circulate inside a water camera, producing a vapor pressure at high pressures. Vapor at very high pressure, which move turbines. Huh?
Yes.
Huh? Yes.
Thank
I
you.
know that this is a consortium very important. Huh?
That's lovely. I'm going to read this for the people. It says here in DSSC efficiency is very, very less. Then it says Professor Anbarasan, conversion and production cost of electricity is costly than other type of renewable resources, I think, and conventional energy sources are available with less cost from fossil and conventional energy. He said then conventional energy sources are available with less cost from fossil. Well,
Yes.
this is true actually.
Yes.
The costs here play a major role actually, and all the resources involved and the amount of very professional people that you need to take to advance the state of the kind of project, which are really, really very high.
Yeah, and you know the solar, Professor Anbarasan, maybe you know it, but the production of electricity coming from photovoltaic devices is becoming very important because there is an important proposal from many state and private institutions to produce what it is named green hydrogen. Green hydrogen. So Chinese are interested to put some hydrogen, green hydrogen factories, both in the northern part and in the southern part, where in this case is produced from eolic systems. You know that the ultraviolet is the most important radiation for photovoltaic cells. But anyway, in the southern part is very windy place, very, very windy, extreme winds, very able to useful for eolic energy production.
That's true, huh?
And so the need of production of green hydrogen has forced or has encouraged the photovoltaic or any other type of renewable energy source to produce clean fuels.
Yeah, they do. On the other hand, Carlo, Professor Anbarasan also said that a need towards solar cells will take a few more decades to come.
Yes, yes.
No, this is
need-based. Necessity is the mother of invention. So in that case, need-based demands only can induce the scientists to go for in-depth research towards the solar cells.
This is very true. Huh? I think, Professor Anbarasan, you are doing a very, very, very exciting research.
Yes.
With many, many applications for the future. Although I'm very old, but I hope that my grandson and that kind of people are going to see these advances. I'm going to make it.
You have to be very optimistic that you are going to be very, very old. You have many years to live, or otherwise that the technology is advanced much more rapidly before you die.
Well, I hope so anyway, because I would like to see.
I guess this is going to be possible. You know that in Chile, many thermal, no, let's say fuel factors producing energy are going to be eliminated, deleted in this moment, many of them. And there is a goal of reducing 50% of them or more in the next 5 years or so. So we are forced to put a lot of effort in improving these renewable energy sources.
Something I would like to say to Professor Anbarasan, we're going to send you a certificate for your splendid participation in this international webinar. And I think that this is the second webinar here. I'm very, very grateful to you. And perhaps, well, what I think I'd rather do is to write to you. I'm going to write to you very, very soon today and let you know what we can do actually. The other thing is that we are planning to launch some special issue of our electronic magazine, Inglo Mayor, and I'm going to dedicate one of the issue for you, one of the volume. And this is going to be something like a tribute for your generosity, friendship, and the quality of the work you have been doing, which is really, really very relevant. My dear professor, I would like to thank you and say that you are a very, very close friend of mine. And well, I'm one of your fans. So please keep on trying very, very hard with your research. And we're going to do the very best of we can do from here. And I hope that in future we will be able to collaborate directly as far as research is concerned. Yes. I have some idea, and you have plenty of idea. So if we amalgamate some of them, we can publish and do something important for humankind. Professor Anbarasan, it has been a great pleasure. Thank you very much for your effort, the energy you have put in your international webinar. And well, everybody will acknowledge you. So I'm speaking on behalf of many, many people who follow you. Thank you very much indeed. Please do remind me to your family, which is very special. I know some about Indian traditions, and well, as you know, I love India, and well, I hope that we shall be able to meet soon. Okay.
So, through this webinar, I congratulate all for this opportunity given to me, and also I wish to do well and be safe for the future. And
also, Professor Anbarasan, also my thanks for your wonderful conference, my acknowledgement to your work. I think it's very, very, very interesting to focus or attack one of the main problems, which is the cost of this type of energy. So my real congratulations and thank you very much for your nice conference. Thank you also to you, Roberto, for your kind invitation to these seminars.
You are more than welcome, my dear friend. Thank you, Professor. And I'm going to write to you soon, today, right?
Okay, thank you.
Bye-bye.
Give my regard to your wife and children. Take care.
Yes.
We all love you, Prof. Take care. Bye.
Yes,
bye.
Take care. And my regards to all family members.
Bye, my friend. Bye.